Swayam Prabha. Digital India. Educated India.
We have been looking at equilibrium of bodies, and in the previous lecture we looked at certain elements and what kind of forces do they apply. For example, we looked at smooth surface, a rough surface, and we saw that on a particular body a smooth surface applies a normal force, on a particular body a rough surface applies a normal force, as well as it is capable of applying a frictional force. Then we looked at a hinge joint and saw that this can apply force both in the x and the y direction, and we looked at fixed or welded joints, and we saw that this is capable of applying a force in the y, in the x directions, as well as it can create a torque. We had solved examples using this, this and this. Now, let me solve an example using a fixed joint. For this, I take a household example of a gate. Which is on two supports like this. Let the weight of this gate be W, let its width be B, let the distance between the supports be H, and let this distance from the support wall to the point where the gate is supported be A. We want to find the forces that are being applied by the wall on these supports, assuming that the entire weight of the gate is borne by the lower support. So, let us see how the gate is being supported. If I look at the gate, it has a weight pulling it down, then the entire weight is being supported by the lower support. So, it has a force F y pulling it up. In addition, there will be forces in this direction. So, let us call this F x 1 and F x 2. These are the only forces that are there on the gate. Then the equilibrium conditions, that summation F x is 0 gives me F x 1 plus F x 2 is equal to 0, or F x 2 is equal to minus F x 1. Similarly, the condition summation F y is equal to 0 gives me that F y minus W is 0, or F y is equal to W. You may ask at this point, how come these two forces F x 1 and F x 2 are generated? It is because F y and W give a couple in this direction, and to oppose this there must be horizontal forces generated at the joint to counterbalance this couple. So, we have gotten these two answers. Let us now look at balancing the torque. So, I have this gate. Here is a force F x 1, and now we have already figured out that there is a force in the opposite direction of the same amount F x 1. They are separated by distance h. Here is a force F y, and here is a force W separated by distance b by 2. So, summation tau z is equal to 0 gives me W times B over 2, that is a couple due to F y and W, should be equal to F x 1 times H, or F x 1 is equal to W B over 2 H. So, the forces acting on the gate are W, W, this way W times B over 2 H, and this way W times B over 2 H. These are the net forces acting on the gate. How about the supports themselves? If I look at the support, this is the wall, this is one support, this is the other support. This support, the upper support, is pulling the gate in by a force F x 1, which is W B over 2 H, and therefore, gate must be pulling by Newton's third law the support in this direction with W B over 2 H. Similarly, on the lower support, the gate is being, let us look at the pushed, gate is being pushed this way. So, therefore, there will be a force pushing the support in with a force W B over 2 H. On the lower support, there are more forces. The lower support is providing a vertical force W to the gate, and therefore, there must be a force W pulling it down. Now, we are ready to calculate forces and moments generated on both the supports inside the wall. So, for the upper support, the only force is this way, W B over 2. So, the fixed support is capable of providing another force, W B over 2 H. It will pull it in with the same force W B over 2 H. For the lower support, situation is slightly more complicated. This distance is A, there is a force W down, there is a force W B over 2 H this way. Therefore, at the wall, with respect to this point, there would be a force to balance the vertical force F y. To balance the horizontal force, there will be a force F x, and there will be a torque tau. Let us see what these values are. So, straight away F x is going to come out to be W B over 2 H, F y is going to come out to be W, and the torque is going to come out to be W times A, but not in this direction, because this is the same direction as the W is providing. The direction would be this way. So, this is the torque generated at the support. So, this is one example of how a fixed support is able to support the applied forces from outside, both vertical and horizontal, as well as a torque applied from outside. Having done all this, let me now solve 2 or 3 examples for you from the book of Merriam. As the first problem, let me take, the problem is like this. We have a wheel on a rough surface, and it is touching a roller which is free to move, and it is fixed to the support like this. We apply a torque tau is equal to 60 newtons per meter on the wheel, such that the wheel does not move. We want to find what is the force applied by the wheel on this support. Let me show the support in blue here. We want to calculate the force on this support at this point. The weight of the wheel is some W. you will see it does not really matter. Since the wheel does not move, therefore, it is a static equilibrium problem. There is a torque like this, wheel would have a tendency to rotate in clockwise direction, and therefore, there would be a frictional force generated like this. The other force would be provided where the roller is touching the force. What about the direction of this force? Since roller is free to move, there cannot be any force in the horizontal direction like this. If there were a force, this roller would start moving. Therefore, the only force is in the direction perpendicular to the surface and in this direction. We are given that this angle is 30 degrees. So, here is this angle 30 degrees. If we now apply the equilibrium conditions, summation f x is equal to 0 gives us, let this force be n cosine of 30 degrees is equal to f, and therefore, the normal reaction n is going to be f divided by cosine of 30 degrees. Similarly, let me make the picture again. Here is the weight W, here is F, here is normal reaction N, here is the torque tau, this angle is 30 degrees. So, we found that N cosine of 30 degrees is equal to F. Summation F y is equal to 0 would give me, if there is a normal reaction N 2 here, N 2 minus N sine 30 degrees minus W is equal to 0. That is the other condition. And the third condition for the torque is summation tau about z is equal to 0. Let me take the torque about the center of the wheel right here shown by blue. If we do that, the torque due to normal reaction N due to this force vanishes. That is the advantage of taking torque about this point, and therefore, I would have F times the radius of the wheel is equal to tau applied, which is 60 newtons meter, and therefore, F is equal to 60 over r. The radius r is given to be 300 millimeters. Here we will write this in meters. So, this is going to be 60 over 0.3 is equal to 200 newtons. So, we have found that the frictional force to support or the frictional force required so that the wheel does not move even after applying this torque is going to be 200 newtons, and therefore, the normal reaction N near on the roller is going to be 200 divided by cosine of 30 degrees, which you calculate, it comes out to be 231 newtons. So, the force by the roller on the wheel is 231 newtons, and therefore, on the roller there will be a force by the wheel of the same amount 231 newtons, and that is your answer. Let us solve one more problem, and this is, suppose we have a block of wood or steel and it is being clamped by tightening the screws on these two clamps. So, here is one screw A, here is the other screw B, and they are being tightened in opposite directions. They tighten to the extent that the force on this block on both the directions, the compressive force is of the amount 500 newtons. If this distance is 100 millimeters and this distance is 150 millimeters, we want to find the forces applied by the screws on these clamps, assuming that the forces applied by the screws are in the along the screw direction. So, let us look at the upper clamp. On the upper clamp, there is going to be a force of 500 newtons in the direction opposite to the force it is applying on the block, and the screw would apply a force like this, let us call it A, and the other screw applies a force in the opposite direction, B. You can see right away I made the forces acting in opposite directions, because that is how I would balance the torque and the forces. Since this is essentially a one dimensional problem, I can straight away write F y is equal to 0, and that gives me 500 plus B is equal to A. This distance is 100 millimeters and this is 150 millimeters. Let me now balance torque about this point, the point in the middle where the A screw is. So, tau Z is equal to 0 gives me 100 times B is equal to 500 times 150, or B equals 750 newtons, and this implies A is equal to 1250 newtons. That is the other problem. Let me solve one more problem, and that is a problem where we support a big drum This is problem 3 on cylindrical rollers. The radius of the drum is given to be 1800 millimeters. Its weight is given to be 400 times 9.8 newtons, that is, it is a 400 kilogram drum. A man of mass 80 kgs starts walking on the drum, and when he reaches here, which is 700 mm distance from the center, the drum starts moving, just begins to rotate on these rollers A and B. The B roller, these rollers are also cylindrical, is capable of applying a frictional force. Roller B is capable of that is why it is only after the man moves a certain distance that the drum starts rolling. We want to find the reactions on A and reactions on NB. To solve the problem, let us make this drum and see what all forces are acting. There will be a force R A acting here, there will be a force R B acting here. The man is at this distance 700 millimeters. There will be a force of 80 G acting this way, and there is a force of 400 G acting this way. The angles are given to be 30 degrees and 60 degrees here. In addition, since the drum has a tendency to rotate like this, there will be a frictional force, let us call it F, at roller B, which is capable of applying a frictional force. Now, we have written all the possible forces that are there on the drum, and let us now apply our equilibrium conditions. So, if we write summation f x equal to 0, summation f y equal to 0 and summation tau z is equal to 0. If we want to find f, that we can do right away. So, let us first apply the torque equation to find f. For this, let us take the center of the drum as our point about which we take the torque. In that case, the only torques that will be coming into picture would be torque due to this weight and torque due to F. If we do that, we will find that torque equal to 0 gives us 80 G times 700 minus 1800, which is the radius, times F is equal to 0. Notice that I did not divide by 1000 to convert 700 and 1800 into meters, because I am using the same units mm on both the forces, and this gives me force F is equal to 80 times 9.8 times 700 over 1800, which comes out to be 305 newtons. Having determined the frictional force F, it is easy to find R A and R B by taking the force conditions. I will leave that exercise for you, but give you the answer, which comes out to be R A is equal to 3770 newtons and R B comes out to be equal to 2352 newtons.